So in a working device, when the device is working in steady state operation, there's always a temperature gradient that happens across the length of the regenerator. And so this is detrimental for device performance because you want the entire regenerator to be operating at max performance. And this leads to the concept of what is called as a compositionally graded regenerator, where the composition of the working alloy is varied along the spatial length, along in the direction of the heat transfer, such that the transition temperature and therefore the magnetocaloric response at each and every point of regenerator is acting at its peak. And so, with that in mind, it's kind of obvious that if you're going to use conventional machining methods, milling, boring, drilling, etc., this will only allow you to limited control over the internal structure. So in our lab, what we do is we use 3D printing, metal 3D printing, in particularly to make these regenerators. And so 3D printing, if you're, and I'm sure most of you are familiar with it by now, it encompasses several manufacturing technologies that build parts layer by layer by now. And each of these technologies, they vary depending on what they can print, whether it is plastic or whether it's metal. It differs in material selection, in terms of the surface finish that you can get, in terms of the durability and the cost associated with manufacturability. But it works. It's great if you want to make something which has a functionally graded design, which is what we want over here, and something which could possibly have less geometrical constraints.